Hello all. Welcome to your asynchronous pre-recorded lecture. I thought, as previously discussed, we would not have a live session this week since I know it gets really intense in the week before residency, especially since our class is on Thursday, the day before residency begins. So I'm recording this. You can watch it at your leisure. There will be a short quiz. The quiz is going to be simply the 5 questions that I ask you throughout the lecture. This won't, you don't have to, it's not blink or you miss it. It's going to be very, very clear when I ask you this because it's going to be your turn and I'm going to give you the problem. If you go to the quiz, you will be able to take the quiz. So let me go ahead and share my screen so you can see what I'm talking about. I'm sharing screen one. Great. So to show you what I'm talking about, I'm going to go to um, modules. And if you go to assignments right here, so you've got home announcements, you go to assignments. The quiz you want to take is this confidence interval quiz. Again, there's 5 questions. It's worth 1 point. It will be the 5 questions that I ask you during the lecture. All right. I'm not trying to make this complicated, I promise. So I know that last time we looked a little bit at confidence intervals, right? And I showed you the Tableau confidence interval, and I sort of said, "Oh, and Tableau is so much better than Excel." I sort of thought about it some more, and I realized I was probably doing the Excel um, confidence interval wrong. And it turns out I was. Here's the confidence interval for Excel. This is here we have the date, here we have the sales. The sales is the y-axis. And anything marked in red, it's probably hard to see. Yeah, it's probably hard to see. Anything marked in red is the forecast. And you've got the upper confidence interval and the lower confidence interval. So I really just wanted to show you that, in fact, Excel can make confidence intervals that are attractive, that are nice to look at, because I know the other one that I showed you was sort of ridiculous. And very quickly, the reason it was difficult to read is because the dates were every single day. So to make it legible, had to do a bunch of manipulation behind the scene for Excel to put it into to aggregate everything at the monthly level. So everything for January is in this dot. Everything for December is in this dot. And then I made a line chart and connected them. So, I still would maintain that Tableau is much easier to make a projection than it is with Excel. But the point of me showing you Tableau and any of these visualization software tools is not that you must use must use Tableau. Tableau is always better. Several of you have already come up to me and said, "Oh, I like using this tool," or I think this one looks really nice. Hey, use those. The point is that I'm teaching you the principles of visualization. Plus, Tableau is at the top of its game. It's at the top of its field. It is a very, very powerful and stylish. It makes a nice presentation. So again, use whatever tool you want. Use the visualization theories and ideas that we talk about in your visualization. I actually have a lecture later on about visualization theory that I'll deliver when we get closer to the final. Okay. As a reminder, a confidence interval, you'd only get a confidence interval of a sample. You wouldn't get a confidence interval of a population because you wouldn't need it. You already know the mean of a population. You know because you have all the data. You just calculate the mean. When you are calculating the confidence interval of a sample, you are saying, I think that within, 95% confidence or 90% or 99% confidence, that the mean is going to be between the upper and the lower intervals, the mean of the true population. So that sounds confusing even to me when I say it. So let's do some examples, and I think hopefully this will make some more sense. By the way, I'm not gonna send this out to people. I'm not gonna go through the steps on how to do this because I know most of you, or a lot of you at least, have Macs, and you cannot do this on a Mac. And also, it's just unnecessarily cumbersome. And you always have other tools like Tableau or other tools that you can use to do forecasts. But if you want to know how I did this, I am happy to, show up during office hours and walk through how I did this. So please let me know if you're interested. It's not all that complicated. It's just a little cumbersome. All right, so let's go to all right, cool. Um, yeah. So I think we so this is a little activity. I'm not gonna obviously this is a recording. I'm not gonna have you break out into groups to do it, but I want to think about this. Um, so I just want to talk about how there's different ways to do things. I think you did this activity in class, so there's just lots and lots of different ways that you can do things, and I think you all had some great examples. So I'm gonna go ahead and jump over to one second. I talked about that there were three types of confidence intervals, right? You've got the confidence interval where you know the standard deviation. And that's pretty rare. And here's the formula for it. We're going to go through all three of these. Excuse me. Use the z value. I have trouble because remember the entire thing you're trying to calculate with the confidence interval is the true mean, the mean of the population. So I sort of feel like, if you know the true standard deviation of the population, don't you know the true mean? Like, don't you know the population? But there may be some edge cases where you do this. And more significantly, this is all we had mathematically before these tools, this t-test tool was developed. This is all we had. This was from a man named Pearson, who's a famous statistician at the end of the 19th century. I think in 1895, he started publishing a lot of tests like the chi-square test and the Pearson's coefficient. So he calculated out, he's one of the people that calculated out all those z tables, all those z scores that we spent so much time on. That's him. The second, I can make this bigger. The second time that you would the second situation for the confidence interval is when you don't know the standard deviation. This is the standard deviation is this is for the population. That is by far the most common, right? If you have a sample, you have a sample of voters. You're surveying 2,000 voters. You don't really, are you going to vote for, Kennedy or Nixon or whomever, right? You don't really know the true standard deviation of the population, how the population is going to vote until after the election, right? But before the election, when you're trying to make your estimate, you don't really know the true standard deviation. So you use this little this little formula, which we will go through. S is just the common signal or symbol, I should say, for the standard deviation of a sample, right? And then finally, we're going to talk about confidence intervals for proportions. And I'll go through examples of all three of these. All right, so apologies, I had to step away for a second. So there are three types of confidence intervals, and this is going to constitute the bulk of the lecture today, talking about the differences between these kinds of confidence intervals. So I want to show, I believe I still have this. Yeah. So we're going to see, go through the first example was where you know the standard deviation. So again, the confidence intervals where you're estimating the mean of a sample. So it's rare that you'd know the sample, the standard deviation of the population, although it's not unheard of. So here's an example. A market researcher is estimating that the mean annual income of her company's customers. They have thousands of customers. She selects 100 of these customers. Oh, sorry, 2 million. I even put it in there. She have 2 million customers. She's selecting 100 customers. It's too expensive to sample the entire population every single time you want to gather more data. So she is sampling 100 of them. She finds the average annual income of these 100 customers to be 80,000. So think about this. You've got 2 million customers. You randomly sample about 100 of them. So what's the percent chance that this mean of 80,000 is going to be close to the population mean? So in this point, from past testing, you know that the population standard deviation is 5,000. So the way you put this into practice, again, you've gathered the mean of the sample. You want to determine a 95% confidence interval for the true mean of the population. So I showed you the formula on the previous page. Here it is again. So I know these are some sort of scary, excuse me. I know these are some scary symbols here, but we know that X bar is. X bar is just the mean. That's all it is. Plus or minus this Z sub alpha divided by 2. So this is by far the newest symbol, the most complex symbol. We'll spend some time talking about this. We talked about it a little bit last week, but we're going to dive into this. And then you have the standard deviation divided by the square of the population. That's what n is. N is the number of observations in your sample. So then we can just fill it in. We've got X bar, that's 80,000. So what's this Z squared? So I'm going to show you something called a t-table. As I said, we've been working previously with a z-table, which everybody loved, everybody enjoyed. So we're going to talk about a t-table now. I'm going to share my other screen. And I'm going to go to screen 2. All right. So here is a t-table. I'll attach this. This should be attached in the email that I send out in case you didn't get it, but it's also in the modules. Okay. So structurally, this looks a lot like the z-table, the z-score, right? We know this z-score. We've been staring at it for a couple weeks now. So let's take a look at this t-table. So again, it looks similar. It's got these numbers down the side here. but it's very different. Um, so let's take a look. Um, it's got this thing, this formula called DF, or degrees of freedom. That's a new term. We haven't heard that term before. Fortunately, it's really easy to calculate. If you know the number of observations in your sample, you subtract one, and that's your degrees of freedom. So if there's 10 observations in your sample, you subtract one, your degrees of freedom are 9. The reason why it's one less is very similar to the reason why when you talk about percentiles, if you ace a test, you get 100% on the test, you're still only in the 99th percentile because you cannot score higher than yourself. Degrees of freedom is the number of other observations which you could pair a single observation with. So if you have 24 observations, once you've paired off 23 of the points, there's no other observations to pair off. So degrees of freedom is always one less than the number of observations. You can see it gets calculated out to individually to about 30, and then it goes up by 10. So, and you can see down here at the bottom, you have the z-score. So the z-score you can only use when you know the full population mean. So imagine you want to know a 95% confidence interval. That's this T sub dot 95. That's 95% confidence interval. You read all the way down, you got 1.645. However, we're going to use um, in this case, if you recall, let me see if I can bring it over. If you recall, I said it's Z alpha divided by 2. So it is a 95% confidence interval, but it could be, you remember, you want the upper and the lower. The true mean could be less than this, or it could be greater than this. So because of that, and it's kind of confusing, I'll definitely admit. So you use two-tailed. Two-tailed is the term for when it can be less or more than the mean. I'm going to try to make it a little bit bigger so you can see, right? So because it is two-tailed, 0.05, you scroll down, and it's 1.96. Now, another difference is what these numbers mean. When we looked at the z-score, we talked about how this was the probability. It's the probability that the value is found in that range, right? So 92% at 1.46, that's going to be to the right of the mean. That's 92, almost 93% of the values are found under the curve. This is not the z-score. This is a t-table. These are not probabilities. They're z-scores. Definitely confusing. I get that. The way these are calculated involves differential calculus. So these are, in fact, quite complicated to calculate, which is why for most of their history, we used these tables. Someone would calculate these tables. Yeah. So to go back to the specific question here, so you've got an average income of 80,000. Because you know the true because you know the true standard deviation, the population standard deviation, because you know that, you can use the z-score. So for 95% confidence interval for a two-tailed test, 95% two-tailed, 0.05, right? Why 0.05? Because 1 minus 0.95, remember it's a 95% confidence interval, is 0.5. So this is the proportion that's not covered under the curve, 5%. 95% and 5% is 1. So you go down here, you can use, you can use 1.96. Yeah, you can also just read down off the bottom, right? This is for a two-tailed test. Pretty simple. You don't even have to read down. I always forget that line's there. So let's go back. So 1.96, and then the rest is just plugging stuff in. 5,000 divided by the square root of 100. So that simplifies to 80,000 plus or minus 1.96 times 500, because 5,000 divided by 10 is 500. Very, very straightforward, right? So that ends up being about 980, right? Something like that. So the confidence interval is 79,020. The actual mean of the actual population, there's a 95% chance, you're 95% confident that the true mean of the population, the true annual income, is somewhere between 79,020 and 80,980. Okay? So you calculate this 80,000. This number to the right of the plus minus, that's known as the margin of error. That's how big of an error you get. So let's take a look at this. So as you go up, oh, sorry, I forget it here. 99% confidence, you're going to have a bigger margin of error. If you want to be 99% confidence, you know, 99% confident, you have a bigger margin of error. So there's going to be a bigger plus or minus. Okay? So you are 95% confident that the true mean of the population is between 79,020 and 89,980. Sorry, 80,980. Think about how this you're trying to estimate the mean annual income. You've just saved a lot of time by only sampling 100 of your customers. You can do all kinds of marketing, this can inform the products you're going to try to sell to your customers based upon their income. Maybe, I don't know, if you're selling insurance plans, that might help you, price out the plans, or any number of subscription services, any number of reasons why you'd want to know this. Okay? I hope that makes sense. So here is the first question. And as I said, it's in the confidence interval quiz, which you can find in the assignments tab. It's published. It's published now. You can do it. I want you to determine a 90% confidence interval for the true mean annual income of the population. So you've got 90,000, you've got the population standard deviation, and you've got the n. This is a perfect square. So this is, if you take the square root of this, it's some whole number, right? You can use your calculators or Excel for that, right? The only difference here is I want you to pay attention to, it's a 90% confidence interval. And remember, you can just read along the bottom of the t-table, okay? So this is the first of 5 questions I'm going to have you do. Oops. You're welcome to pause the recording, go do it, or you can do it at any time. I'm going to give you a week to do it. I'm going to stop sharing, and I'm going to move this over to here. and we're going to talk through some of the theoretical basis of this of these t values. What exactly are they trying to say? So the student's t distribution. So t is a family of distributions. For the most part, if you don't know the population standard deviation, this t of alpha divided by 2 is going to depend upon the degrees of freedom. You remember that t table? As you got more and more degrees of freedom, the t table started to look closer and closer to the z-score. So the t-score is closer and closer to the z-score. So I'm going to bring this over. And the t-score is only used, the z-score is only used when you know the full population. Although when you get to 1,000 degrees of freedom, it's pretty close, right? Look how close these are. So let's think about what this would look like in practice, maybe with some examples. So um, imagine that, yeah. So the degrees of freedom is the number of observations that are free to vary after the sample mean has been calculated, and it's always n minus 1. If you don't understand the theory, just remember it's n minus 1. Excuse me. Ooh. So imagine that. So here's like maybe I'm going to walk you through. Hopefully, you can kind of understand why degrees of freedom, right? So imagine you know this. You know that the mean of three numbers is 8. You have your first observation, the value is 7. The second observation, you know uh, the mean is the value is 8, right? The first is 7, the second is 8. So how could you calculate x sub 3? So if you know the mean of these three values, it's 8, then x sub 3 has to be 9. It has to be. If you know 2, x sub 3 is not free to vary, right? You know it. So whereas if you only knew that it was 7 as the mean, these other two could be any. So here, n is going to equal 3. The number of observations is going to equal 3. So the degrees of freedom is always n minus 1 is 2. Two values can be any number, but the third is not free to vary for a given mean. Again, if that is difficult to parse, and I totally get it, just remember the degrees of freedom is n minus 1. That's all you have to remember. So what, let's take a look at these t distributions, right? So all these distributions are a normal distribution. So we've got three curves here. We've got this kind of lighter green, tealy kind of color. We have a normal standard deviation. The mean is 0. You can use the z-score, so the degrees of freedom is infinite because you know the true mean. And t distributions look a lot like it. In this one, you have 13 degrees of freedom. So you have how many observations? 14 observations. It's a little bit more spread out than the standard, and it's a little bit fatter than the standard because there's a little less certainty. There's less certainty, so it's more spread out. There's fewer values that are concentrated around the mean because the mean is uncertain, right? Degrees of freedom 5, it's even more spread out and fatter. So they're bell-shaped and they're symmetric, these t distributions, but they have fatter tails than normal. They stick out more. They're more spread out. And the inverse is also true. as t gets closer and closer to z, the n as the n increases, it looks more and more like the standard deviation. So here's that example. We talked about there's three observations. So imagine you have three observations, n equals 3, doing a 95% confidence interval. Okay? So you're going to look up that score that you can use. So, do I still have it over here? Yeah. So we've got a 90% confidence interval. We've got two tails. So two tails, meaning it could be less or it could be greater. Could be less, could be greater. So 0.9. Does that make sense? Because it's a 90% confidence interval. So sorry, 0.1, I should have said, that's the value you want to do, two-tailed, 0.1. So you've got three observations. That means 2 degrees of freedom. So the value you'd use is 2.92. Now imagine how much different that is from 1.645, right? It's just so much less. And this reflects the uncertainty. It's fatter, it's spread out. You're less certain what the true mean is. So you have to stretch out your confidence interval to get the true mean. So that's how I got this 2.92. And again, just a little note here. This is t-values. They're not probabilities. This is the result of intense differential calculus calculations. And the reason differential calculus is because, as you might remember, the area under a normal curve is 1. If you've taken calculus at all, you might remember, or you might not, that the integral is the area under the curve. So to calculate these t-values, um, it's a lot of work. I actually don't know how to do it myself, so I'm just going to admit, I'm sure we could all look it up and sort of labor through, but the question is why? And here I want to sort of break and give you a little bit of a history of what these why are they called students' t-table? What is happening in the first place? So this whole concept of the normal distribution, sorry, let me stop sharing. This whole concept of the normal distribution has been around a very long time. It was first invented, or first derived, I should say, in 1733 by a French mathematician, de Moivre. My French is terrible. I'm so sorry. But again, this was derived a very long time ago. And the frequency calculation, to calculate the frequency distribution, is some truly complex calculation that a mathematician named Gauss came up with. You probably don't really need to know that. So, as I said, there was a mathematician named Carl Pearson, a statistician, who calculated out all those z-scores. And so pretty much if you wanted to guess if you wanted to do calculations, you had to use the population. But if you don't have all of the values in the population, you have a sample and your certainty is less. Your certainty goes down. So, what was I going to say? So Carl Pearson came up with these z-scores in, I believe, 1895. I've got it in this thing, somewhere around there, 1895, a long time ago. So then in 1905, a mathematician named William Gossett in London started developing the t table. And he calculated these t values for the number of observations, I believe between 4 and 10, if there were observations between 4 and 10. And it took him 6 months to calculate by hand and with a kind of mechanical calculator that was in use at the time. Certainly not even as powerful as a calculator today, but a big help, right? So that's 1905. He comes up with these. And the last kind of question is, why did he call them the student's test? The reason is William Gossett he worked for Guinness, the Guinness Brewing Company in Ireland, and they were just entering the era of kind of mass production, and they had this market domination in beer, and they wanted to keep that market share. And they realized as they were producing more and more that they would need some standardized samples. So they hired this British statistician, Gossett, to help them, develop statistical rigor around their samples. Just exactly how precise did all their samples of yeast and all these other technical details of brewing have to be to produce consistent final output of beer? And so Gossett, again, he spent a long time calculating out all these values, but when he published it, I believe he published it in like what is it's kind of Biometrica. That was the journal. Published it in Biometrica in 1908, and he published it under the pseudonym of Student. And the reason he did not use his own name was because at that time, uh, companies did not want to have their name attached to these any kind of publication. They were afraid it would lead to trade secrets. People could figure out, oh, this is Guinness, and they could sort of work backwards and steal sort of trade secrets. This was cutting edge mathematics at the time. And I just want to say this sort of varies from today with AI, another cutting edge tool. I read a lot of Anthropic papers published by Anthropic, incredibly technical papers. They're white papers, but they're every bit as technical and rigorous as a scientific paper published in a journal. And companies these days want their knowledge and their expertise to get out there, but in those days they didn't. So Gossett had to publish under a pseudonym, which he chose as student because it was like the textbook he used in college. It was like the student's science notebook. So he just published under the pseudonym Science. Eventually, when other mathematicians like Carl Pearson realized how valuable it was, he became famous enough, and people knew who he was. But for a while, it was unknown. Anyway, I think that's kind of fascinating, but maybe you don't. All right, let's go ahead and share my screen again. Hmm, There we go. All right. So actually, you know what? I think I actually want to share the whole screen. My mistake. I shared just that one page, but I think I want to share the whole screen because we're going to be looking back and forth at the T table. Okay. So yeah, if you want to get this T score, you don't have to look up in this table. I promise you. If you find this table so confusing, I would invite you to take your time and try to look at this table, try to make sense of it. But if you absolutely can't, and if you figure it out and you're like me and you forget later on, uh, you're always going to have this value right here in Excel. It's t.inv dot 2t. The 2t stands for two tails, right? So all you need is the alpha and the number of degrees of freedom. So I think I have a little thing where I did it up here. Yeah. So I sort of wrote it out here. I think this is just some junk. I'm going to delete that. Yeah. So remember, you've got a 90% confidence interval. 90%, because that's what we told you, 90%. You've got that makes an alpha of 10%, which again is 1 minus 90%, 10%. You have observations. This should not be a percentage. It should just be a number. You have 3 observations, which means 2 degrees of freedom, right? And minus 1 degrees of freedom. So here's the formula for it. Let me make it bigger. So here's the formula for it. T dot inv dot 2t. I don't know what the symbol for alpha is, so I just put an A in here, comma degrees of freedom. So the alpha here is 0.1 and the degrees of freedom is 2. So again, I don't know if you can read this, but this says equals T dot inv dot 2t. And for the alpha, I put in this B2, which is 0.1. And then for the degrees of freedom, I put in 2. That's the formula sort of broken down here. And that gives 2.92. So that's the exact same thing as, where am I here? This, right? 2 degrees of freedom, two-tailed. Here's your alpha, 0.1, right? 2.92. Hopefully that makes sense. So that's 2 different ways to find this t-value, which you're going to need to calculate your confidence intervals. Okay? All right. So I said that there were 3 scenarios. Scenario 1 was if you know the population standard deviation, fairly rare. The much more common scenario is where you don't know the population standard deviation. So here, imagine you've got the mayor of a big city and they need to hire a bunch of new employees and they're trying to standardize their processes, right? So they want to know how much training do new employees need, or how much training do city employees need every year? And this is all kinds of things, right? Technical training and whatever other kind of training you need. So um, he asked them, hey, how much training do you take per year? So he takes a random sample of 25 city employees. They say, oh, you know what? I need an average of 8. I need an average of 50 hours of training per year. That's your X bar right here. I go through an average of 50 hours of training every year. I got to do the no harassment training. I've got to do the cybersecurity training. I got to do the job training, all this kind of stuff, 50 hours. And he calculates the standard deviation of that sample. We know how to calculate the standard deviation of that sample is 8 hours. So there's some deviation in there, right? So how would you go about calculating a 95% confidence interval for the true mean of the population? Okay, remember it's always going to be centered around 50. So let's take a look. We need 3 things. We need the number of observations so we can get the degrees of freedom. So in this case, there's 25 observations. 25 minus 1 is 24. That's the degrees of freedom. Next up, 95% confidence interval. I know it's slightly confusing to see this 0.025. Melissa, why do we see 0.025? That's because half is below and half is above. Think about that distribution curve. 95% of the area of that curve is shaded in, but you've got 2.5% on this side and 2.5% on this side that are not shaded in. So I got this thing that's 2.0639. How did I get that? Well, you could always use the t.inv.2t, or you could look at this. So again, 95% confidence interval, but it's two-tailed, right? Two-tailed right here. And we have 24, sorry, I lost my place. You got 24 observations. It's here. So 25 observations, 24 degrees of freedom, 2.064. So it's just rounded, right? And if you want to calculate it in Excel, in this case, the alpha is, so let's just try. We say equals t dot inv dot 2t, right? Two-tailed t-test. All you need is alpha and the degrees of freedom. In this case, it's 0.05 because 95% confidence, there's a 5% unknown, right? That's the alpha, comma, the degrees of freedom. In this case, it's 24. Let's take a look. 2.0639. That's where I got this number from. Excel is your friend. It can do all this stuff for you. The table is your friend. It can do all this stuff for you. Don't knock yourself out. Whichever one works for you, use that method, okay? All right. So back to our slide. So now we've got the degrees of freedom. We've got that t-score. And we already know the mean of the sample. So we'd write it like this: X bar plus or minus this t-score, which is right here, times the standard deviation divided by the square of the number of observations. So X bar is 50. It's right there. X bar is 50. It's the mean of the sample. The t-score here is 2.0639. You could use 2.064. That's totally fine. You don't have to be that precise, but 2.0639. The standard deviation is 8, and this is the number of observations. The square root of that is going to be 5. So you can check this calculation. 8 divided by 5 is 1.6. And that gives you this portion right here. That's called the margin of error. So roughly, you know that 2 times 1.6 is going to be about 3.2, right? Roughly. So, but calculate it out. So you get some number, you subtract it from 50, you get 46.698. You add it to 50, you get 53.302. Don't believe me? Oops. So we calculated this, right? And we know that 8 divided by the square root of 25 was 1.6, not percent. Sorry, it's because I need it as a number, not as a percent. Just give me a second here. Come on now. Number 1.6. And we know, so that is this portion right here. So equals this times this gives you, I'm so sorry. This is really annoying. I'm going to take off the, just going to take off the, make it a number. I have to stop sharing. It won't let me do this while I'm sharing. Super annoying. All right. So, yeah, I'll go back to, and I'll share again. Always torturous to use Excel on this computer. So, this is just the t-score plus that's just 8 divided by 5, 1.6, or 8, which is the standard deviation, divided by the square root of 25, which is 5. So 8 divided by 5, 1.6. And you know that the mean here is 50, right? So 50 minus this equals 50 minus, come on, why are you being like this? Equals 50 minus this, right? That's the lower range, and then equals plus this. So you know that the true mean, there's a 95% chance that the true mean of the population of city workers, the number of hours of training that they need every year, the 95% chance that it is somewhere between 46.7 and 53.3. And that's what I'm conveying here. This is a little more, listen, if you can do something to two decimal places, that's fine with me in my, I'm not going to ding you. This is not elementary school math, middle school math. I'm not going to ding you for significant figures. Don't worry about it. Okay? Okay. Question number 2, I want you to determine a 99% confidence interval for the amount of training provided to city employees. Again, 99% confidence interval. You've got the number of observations, you've got the X bar, you've got the standard deviation of the sample. You can either use the t-table or you can use the Excel formula. T.inv.2t. All you need is the alpha and the degrees of freedom. All right. As I said, there's 3 types. We have where you know the standard deviation of the population, where you don't know the standard deviation of the population, and when you're using a proportion. So the confidence interval for the proportion, fortunately, you can use the z-score. It's right there for you. It's not hard. You don't have to look up anything. You don't have to worry about degrees of freedom. Don't worry about that. You have the assumption that if the sample is over 5 observation, it starts to approach a normal distribution curve. So again, you should have a sample of 5 or more in your proportion. I think that's usually not a problem. So here's what it looks like. This is some new symbols here. We've got this uh, uppercase pi. That's all that is. It's uppercase pi. Nothing looks kind of like the lowercase pi that we're more familiar with. Nothing too fancy. Uh, Uppercase pi minus 1 times 1 minus uppercase pi divided by the square, but divided by n. So you can just, this is the whole formula for the confidence interval. P is the proportion. P is the proportion. Plus or minus the z-score. P, 1 minus P divided by n, provided that the number of observations, I should have just had this as n, the number of observations is 5 or greater. So I wanted to choose some election data because elections are things that where we see this a lot, right? You see they will poll people in different studies, different polls, and they'll give both a percent, as I'm displaying here, and a margin of error generally. Not always, they don't always provide, but they'll say like plus or minus 3%, something like that, right? So this is data from the Democratic presidential primary in, I guess, June of 2008. So right before the primary, it looked like Barack Obama. Um, 52.8% of people said they're going to vote for him. 40.6% of people said they're going to vote for Hillary Clinton, and 6.6 voting for somebody else. This is like Edwards or I don't know who else, right? I can't remember who's running there. Um, I think yeah, I don't know. So, right, right. So this is a proportion. So we're going to estimate the confidence interval of Obama winning or Clinton winning uh, using that proportionality formula. Here is another. I just looked this up. I pulled this off of Real Clear Politics just last night. This is the 2026 um, Senate race with, I think, Mike Collins versus John Ossoff. John Ossoff is projected to win, but it's tight, right? It's 2.3%. It's within the margin of error. So there's this 2.3%. This is all these polls together. You can see the individual polls. We've got this, whatever TIPP is. We've got Signal and we've got a Trafalgar Group poll, the dates that they were taken. That's July 28th of this year. That's not July 2028 or anything, right? And what's this mean? This is the sample size. So this poll sampled almost 3,000 voters at a margin of error about 1.8. This one sampled only 800, has a larger margin of error, and this sampled about 1426. It's got a margin of error that's in the middle. And in general, with a well-designed poll, the margin of error is going to be less the more people you sample. And that makes intuitive sense, right? As you sample more and more people, you get a better sense of the how the population is going to vote. Eventually, if you know the population, there's no margin of error because you know everybody, right? All right. So back to that Obama. I just wanted to show you the margin of error thing. So back to this Obama voters, right? From we did on the slide before. So imagine that that poll was based upon 1,230 likely voters. This is the 2008 Democratic presidential nomination between Barack Obama and Hillary Clinton. 52.8 of 52.8% of voters said they're going to vote for Obama. So let's calculate a 95% confidence interval for the true proportion of Obama supporters, right? So let's take a look. So as a reminder, here's the formula. P, which is 52.8, Z scored, or I'm sorry, Z, you can use the Z score. 52.8 times 1 minus 52.8 divided by N. So that's 0.528 minus 1.96. That's the 95% confidence interval. You can look it up on the T-table. Again, you're using the Z-score times the square root of 0.528. Oh, I actually did this wrong, huh? I think that's embarrassing. This should be like 47.2. Well, my mistake. Uh, yeah, whoops. That's very funny. I was changing these around a lot. I don't know. That's funny to me. I don't know why that's so funny to me. Oh well. This is what happens when you work on these too late. 1 minus 0.528. Um, yeah, 47.2. So I'm going to change these so then when I give this to you, you won't have this obvious wrong answer here. So 0.472. All right. So let's take a look. And this is going to be slightly different. I'm going to copy this. I'm going to put it into Excel, just my little scratch pad of Excel. Probably won't go all the way through, right? But let's see if it'll work. It says no. Okay, no big deal. 0.528 minus 1.56. Oh yeah. Times the square root. Uh-huh. You've entered too many arguments. What did I enter? Now let's do this. There we go. No, I don't think I did. Oh, that's right. It does not like commas. So we get 0.50. Wow. Okay. So the lower, so again, remember 52.8%. The lower end is going to be just basically 0.50, which means the upper end. So let's just go back to here and let's change this to a plus 55.59. You can also calculate just this is called the margin of error. You got a margin of error of 2.8%, 2.79%, right? So what was that? 555. Yeah, so we'll say 0.56. I'm not that concerned. 0.56, right? So let's go ahead and write that out. So our lower confidence is 50%. Our upper confidence interval is 56%. But we just want to check to make sure that their NP is greater than 5. So that is simply 1230 times this. You get that's bigger than 5. And I need to change this. Yeah, I did this one right. Hey, look at that. Is 580. So that's also bigger than 5. So this checks out. I think this math is wrong, but you get it, right? What's 1230 times 0.72? Good math. Oh yeah, it does not like commas. Let's see if this works. 580.6. Yeah, right. I got the right answer. Okay. Um, 649. All right. This should be 649. That's why I looked wrong. All right. So we're 95% confident that the true mean is going to be between 50% and 56%. 56%. Right? Does that make sense? That makes sense to everybody. And that means although the interval from 50% to 56% may not contain the actual proportion of voters who are going to vote for Obama, because we only sampled 1,230 actual voters and way more people are voting. We believe 95% of the intervals formed from sample sizes of 1,230 in this manner will contain the true proportion. Thanks for hanging in there. Let's do our third question. Calculate a 95% confidence interval for the true proportion of people who enjoy pineapple on pizza. You probably saw that. That's fine. Totally fine. You should probably still work on it yourselves. All right. So we've got a 95. So I want the proportion of people who like pineapple on their pizza. That's 44%, a 95% confidence interval, and you have 1,000 people that you surveyed. This is an actual study that some marketing company did. I don't know how rigorous the study is, but they did ask 1,000 people, or 3,000 people, I should say. But just use 1,000 for this. Just use 1,000 for the purposes of this Okay, cool. Yeah, and then think about what I mean by the margin of error. All right, so that's question number three. So the next question I want to answer is how big, how do you know if you got enough observations? How big is big enough for your sample? Whenever you're doing this estimation, you want to make sure that you use a big enough sample so that you can calculate your confidence interval that's worthwhile. Again, um, that t-table goes down to like one observation, but that's really bad practice, bad form to try to estimate the true sample, true population mean uh, from one observation point. And you can sort of see that at one observation, a 95% confidence interval, 12.7, right? So imagine that it's 1.96 if you got the z-score. That confidence interval is going to be huge. And that makes sense because you have very, very few observations. So the margin of error, um, that's that portion after the plus or minus sign. That's also often called the sampling error. Okay. So here's the formula for the confidence interval. This sampling error is the amount of imprecision, the amount of guessing, the things you don't know in the sample, in the estimate of the true parameter, right? So that's just this portion. Again, like I said, the portion to the right of the plus or minus. That's this. So if you solve this for n, you're going to get, so, multiply both sides by square root of n, multiply both sides by square root of n, divide both sides by e, square both sides, you're going to get this. N equals this z squared, standard deviation squared, divided by e squared. Okay? So what you're trying to figure out is how many, it's the sample size. How big of a sample do you need? So that's why you're calculating, solving for n here. So here's how you would do that. That's for the population. Imagine you want to do this for a sample, right? So you want to figure out your desired confidence level, right? Whatever the sampling error is, I want it to be within, I want you to figure out um, how many people are going to vote for Barack Obama to within 2 percentage points. So you want to figure out how many people you need to sample, right? Before you can get it within those 2 percentage points. And you'll also need the standard deviation, which you can calculate. Okay? Yeah, if you are, um, again, if you don't know the standard deviation, you can just calculate it for the sample, but you just want to make sure it's large enough, right? Right? You just take the estimate of the sample, the standard deviation of the sample, right? And in here is the formula. So let's put this to practice. So you want to look at the average property tax paid per capita, right? Within $300. So you are a county worker and your boss says, I want you to estimate the average property tax that people pay within $300, plus or minus with a 95% confidence. You believe, based upon your previous expertise or your knowledge, that the population standard deviation is 1,000. So how many individuals do you need to survey? Well, this is, the population standard deviation, so you can use the z-score. The z-score for 95% is 1.96. So 1.96 squared, you got the standard deviation squared. That's this ginormous number. and then you divide it by this E, the margin of error that you need it close to, and that gives you 42.7. So the um, to estimate the local property tax to within 300 of the true mean, you need to sample 42.7 people, or round up 43 people, right? You can't sample a half a person, a zero point 0.7 of a person, right? So you always want to round up. Make sense? So this is the fourth question. You want to estimate the property tax paid per capita within 200%, or sorry, within $200 with a 99% confidence interval. So you can pretty much just use this formula. Just find for 99% here, it's the same, um, it's a different standard deviation. Sorry, it's a different standard deviation of 2000. So 2000 instead of 1000. And you want to, and the margin of error you want is 200 instead of 300. So just plug in those values. You will get some value. Is it 680, 664, 625, or 640? This is question number 4 in the quiz. You can go ahead and do that. And then let's talk about the sample size for a proportion. So you need the level of confidence, whatever sampling error. Again, I want to get this to within 2 percentage points. And the proportion of the events of interest, which is pi, right? Generally, you don't know pi, or you wouldn't need to do the study. You don't know really what percent of people are going to vote for Barack Obama, but that's why you're doing the study, right? So you do this, you create this sample, you poll however many people, and you estimate pi from that, right? So that looks like this, z squared. This looks a lot like what we've seen before, right? So the number is n, z squared times pi minus 1 minus pi over e squared. So the CEO of Shell Oil believes that 15% of people rate oil companies favorably. You want to test this, and you want to be 95% confident within 3 percentage points. So 15% is not that high, right? CEO of Shell is that's what he believes. So how many people do you need to survey? So let's put that in the old machine. Again, 95% confidence, that's this z squared. 15%, here's your statistic of interest. So 0.15 times 1 minus 0.15. And then divided by the margin of error, 3 percentage points. That's 0.03 squared. And that gives you 544, or you probably always want to round up. So that's 545 people you want to sample. So the final question is same basic scenario. This time the CEO believes that 20% of people rate oil companies favorably. You want to test this. Do they really? I don't know. Let's test it out. So you want to be 90% confidence that the true mean is within 5 percentage points. How many people do you survey? So again, just substitute it out. 90% confidence, that's a different number. That's not 1.96. 20% instead of 15, and 5% instead of 3. This is question number 5 in the quiz, and that's the final question of the night. So we talked about the confidence intervals for the means and the proportions. We calculated some confidence intervals. We hopefully interpreted them. And we looked at how many sample sizes you need to get a means within a certain margin of error, and we calculate those. Okay, thank you very much. Again, don't forget to complete the quiz. And I will see you on Friday. All right, thank you so much.